Hello everyone, this video is going to cover rotational kinetic energy. Just like with the other types of angular variables we've talked about so far, if we know the proper equation for translational motion, we can find the equation for rotational motion by substituting in the angular variables. So we know that translational kinetic energy, having to do with the motion of the entire object through space, equals 1/2 mv squared. That means that to find an expression for rotational kinetic energy, we would just substitute in the angular versions of m and v, and so we replace the mass with the moment of inertia I, and we replace the speed with the angular speed omega, and so we get the rotational kinetic energy equals 1/2 I omega squared. If we have an object that is both translating and rotating, so for an example, an object that is rolling, that object is going to have both translational and rotational kinetic energy, because the object is both moving through space as a whole and rotating about an axis. And for the typical symmetric objects that we're going to be talking about, we have a translational kinetic energy 1/2 mv squared. I'm going to use a subscript cm there, referring to the center of mass. So when we talk about the speed of the object, remember that different parts of the object will have different speeds based on their rotation as well as how they move through space as a whole. So we want to specify there is the velocity of the center of mass. We're referring there to how the entire object moves through space. And then we would add on the rotational kinetic energy, 1/2 I omega squared, and there note again we're using the moment of inertia for an axis that goes through the center of mass. If we think about, say, a rolling sphere, we would see that the object is rotating about its center, and for a uniform sphere, its geometric center is the location of its center of mass. So we can now think about conservation of energy problems for objects that are both moving translationally and rotating. So for instance, let's come back to a problem that we dealt with earlier in the year of an object moving down an inclined plane, but now rather than it being just a point particle or say a box sliding down the plane, now we're going to have an object that is rolling down the plane. And to start, let's say that we have a solid cylinder of mass big M and radius big R, rolling without slipping down an inclined plane. And we will say that the center of mass of the cylinder starts at a height h above where it will be when it gets to the bottom of the plane. So overall, the cylinder We'll drop a height h from where it starts. And we want to find an expression for the center of mass speed at the bottom of the incline. So this would be a conservation of mechanical energy problem, just like we dealt with earlier in the year. The sum of the kinetic and potential energies at the top of the incline equals the sum of the kinetic and potential energies at the bottom of the incline. And I should assume that the cylinder starts at rest. And so then we know that the initial kinetic energy is 0. When it gets to the bottom of the incline, that is a convenient place to set the gravitational potential energy to 0. And so just like earlier in the year for an object sliding down an inclined plane, we have the initial gravitational potential energy being converted fully into kinetic energy. However, here again we need to be careful that there are two terms to the final kinetic energy. There's both the translational kinetic energy, 1/2 mv squared, and the rotational kinetic energy, 1/2 I omega squared. So we have our initial potential energy, mgh, that equals 1/2 mv squared plus 1/2 I omega squared. We can look up in the table on page 210 of the textbook that the moment of inertia of a solid cylinder rotating about a central axis is 1/2 mr squared. Notice that we can factor out an m on the right-hand side, and so all of those m's will cancel. And furthermore, if the cylinder is rolling without slipping, then we know that the center of mass velocity is equal to r omega squared, is equal to r omega. And so r squared omega squared is equal to v squared. Plugging that into the equation above, we then have gh equals 1/2 v squared plus 1/4 v squared, or gh equals 3/4 v squared, which would give us that the speed of the center of mass at the bottom of the incline equals the square root of 4/3 gh. And you may remember from earlier in the year, for an object just sliding down an incline without friction, where the speed equals the square root of 2gh. Here the cylinder is moving slower at the bottom of the incline than an object sliding down the incline without friction would be. But again, thinking about it from an energy standpoint, if the object is just sliding down the incline without friction, all of the initial gravitational potential energy is being converted into translational kinetic energy. All of that gravitational potential energy is going into motion of the object through space. Here, not all of that energy is available to go into translational kinetic energy. Some of it has to go into how the object is rotating. And so it does make sense from an energy standpoint that this cylinder rolling down the incline would be moving slower at the bottom than an object simply sliding down the incline without friction. Similarly, we can see the shape of the object has a big impact. The expression for the center of mass comes in for the moment of inertia about the center of mass comes into play here. And so let's say that instead this was a solid sphere. Same mass, same radius. We can again look up the expression for the moment of inertia. We can see that for a solid sphere, it is 2/5 mr squared. We would end up with a similar looking expression, but the coefficients aren't all going to be the same. We would then have mgh equals 1/2 mv squared plus 1/2 times 2/5 m r squared omega squared. So a 2/5 in this rotational term rather than another 1/2 as we had for the solid cylinder. Again, the m's cancel. R squared omega squared equals v squared. And here we have gh equals 1/2 v squared plus 1/5 v squared, or gh equals 7/10 v squared. So v equals the square root of 10/7 gh. And 10/7 is a little bit bigger than 4/3, and so this solid sphere would be moving just a little bit faster at the bottom than the solid cylinder would. Accordingly, the solid sphere and if you put the solid sphere and the solid cylinder side by side, release them from rest at the same time, the solid sphere would get to the bottom of the incline a little bit sooner than the solid cylinder would. The larger the moment of inertia, the greater proportion of the kinetic energy that is going to be rotational kinetic energy. The smaller the proportion that is translational kinetic energy, the slower the object will move, the longer it will take for it to get to the bottom of the incline.